Hi, everyone. My name is Sanjat Kanjilal. I'm a group leader in the microbiology informatics team at the Amsterdam University Medical Center in the Department of Medical Microbiology and Infection Prevention. Thank you very much for the opportunity to speak at the second AI and infectious disease workshop. I'll be talking today about how to leverage AI to perform multi-center analyses with microbiology data. This may be self-evident to people, but I think it's important to be explicit about why a multi-center approach to microbiology data analyses is an important advance over single-center approaches. The first is that it gives greater insight into how pathogens behave, not just their transmission, but also what types of patients they infect, what syndromes they cause, how are they diagnosed, et cetera. Secondly, having data across a wide geographic area means earlier detection of spatiotemporal spread across a region. Third, it allows for identification of cross-kingdom interactions. And here I'm thinking about the rise of RSV and invasive group A streptococcal infections, for example, that occurred regularly with the easing of pandemic lockdowns. Fourth, the larger sample size of multi-center analyses allows for better definition of the effects of pathogens on small subpopulations. Finally, this structure allows the use of more quote-unquote data hungry or AI models for their innumerable applications. However, data sharing and analysis is really challenging. I think we all know this again. There are issues around how to harmonize highly heterogeneous data streams, how to build secure linkages between health systems, how to govern that whole relationship, how to maintain privacy for all patients contained within the data set, while still being able to perform robust analyses, and of course, how to fund these endeavors, which will require resources dedicated to it by all the affiliated parties. And there's no single way to do it right. I list 4 aspects of multi-center analyses that determine its scope and complexity. The first is the frequency of data exchange. The second are the types of data being exchanged. The third is a method for harmonizing data across centers. And the fourth is the type of analyses that will be performed on the harmonized and cleaned data. Towards the top of this figure are the simplest scenarios, and the bottom has the most complex scenarios. As an example for the frequency of data sharing, the simplest will be periodic exchanges occurring a few times a year in batches, while the most complex will be continuous real-time or near real-time sharing. In terms of data types, the simplest are structured data, such as what comes in tabular format. The next most complex will be unstructured text, such as what is found in clinical notes or imaging reports. The most complex are actual image stacks or movies. For data harmonization, the easiest, the most time-consuming will be for manual mapping of data to a common set of categories or data types. Slightly more complex will be to use a set of rules to do this, and the most complex is to automate this entirely using AI. Finally, analyses range from simple descriptive statistics, such as means, variances, t-tests, etc., to traditional regression models, to multimodal modeling using AI prediction and inference algorithms. I would focus on the second most complex case today, which is continuous data sharing with structured and unstructured text using automated harmonization methods to support advanced AI analyses. And that's a very ambitious goal. So why choose this scenario? And I give you 4 reasons why. 1, it addresses the most complex real-world challenges that exist out there right now. 2, the necessary technologies to do this have now finally matured. 3, it represents the cutting edge of pathogen surveillance and monitoring, which is a key function of any health system. And 4, if we can solve it using this method, simpler approaches and tasks become much more straightforward. My proposal to do this leverages 3 technical advances that have matured over the past 2 decades. The first advance is the development of common data models for healthcare. This approach takes advantage of pre-existing global standards for structuring healthcare data. This ensures there's semantic interoperability across institutions and also that syntax is recognized and usable for external audits. The second advance is the emergence of large language models, which allow for automatic extraction and mapping of concepts in structured and unstructured form to fields located in a common data model. The third is a federated learning approach to analyses. And the idea here is to transport the model to each health system in a federated network rather than pooling data in a central location. And this helps address many of the privacy issues that limit sharing of sensitive health information. So I will go through each of these pillars one by one, starting with common data models. The traditional approach to sharing data in the past has been for a human or a group of humans to build custom mappings for every data exchange. There are multiple drawbacks to the approach that I list here. One, it limits the generalizability of this because usually the mappings are custom made just for that analysis. Two, there's an exponential growth in complexity. It's an n squared problem as more data is added. Three, it breaks every time there's an update in the way things are mapped. And four, it's really not sustainable for continuous data exchange, which requires continual remapping. The common data model approach takes advantage of decades of work done by the informatics community to build globally agreed upon ontologies for medical concepts and then map them to discrete fields. By using these existing frameworks, we can both improve generalizability and greatly reduce the effort required to manually generate a new set of mappings. It promotes automated analyses and deployment since many software packages rely on existing common data models. And as mentioned before, since common data models are recognized by regulatory authorities, it facilitates compliance and auditing. The examples I will provide in this talk pertain to virology, but apply equally to bacteria, fungi, parasites, and other types of infectious diseases. Probably the most popular common data model is OMOP, which stands for the Observational Medical Outcomes Partnership. It is supported by a large international community of healthcare informaticists known as Odyssey, and is really good at longitudinal profiling, which, for example, will be very helpful for cohorts of patients with HIV. Like everything, it has its weaknesses, which I will discuss, but overall, it is the most common CDM used in healthcare systems around the world. OMOP incorporates many existing vocabularies like LOINC, SNOMED-CT, and RxNorm, which makes it even more versatile. FHIR, which stands for Fast Healthcare Interoperability Resources, is another example by which data is shared across institutions. It is HL7 compliant, meaning it meets privacy standards, and is excellent for real-time exchange of data. It is also very flexible, but that is actually its greatest drawback. It is so generic that each use case requires manual building of something called profiles, which sort of defeats the purpose of a common data model. I only mention it here because it is also commonly used in healthcare systems. Finally, there's MixS, aka the minimum inhibitory about X sequence. This is a common standard for sharing genomic data and will be essential for genomic epidemiologic analyses. My recommendation for this will be to do multi-center work using a hybrid of OMOP plus MixS to share data for the reasons I just stated. Some key tables in OMOP that are relevant for virology include the measurement table, which contains viral loads, serology results, CD4 counts, CT values, etc. The specimen tables, which contain information about the specimen type, the observation tables, which contain virus names and characteristics like variant class, and drug exposure tables, which contain names and doses of anti-infectives that the patient may receive. For specialized use cases, additional tables can be built, which are called extensions. For viral surveillance, they would include viral variant tables containing spike mutations for SARS-CoV-2 or integrase inhibitor mutations for HIV. Phylogenetic relationship tables are necessary for analyzing relatedness, transmission cluster tables for tracking patterns of transmission, vaccination status and response tables are necessary for establishing infection susceptibility. To give a concrete example, I'm showing what a phylogenetic tree, node, and cluster table would actually look like, and this is written in SQL. The details are not that important, but just for illustration purposes, you can see, for instance, that the tree table has fields for the type of tree, for instance, maximum likelihood, and an entry for the full tree in Newick format. The node table links to the tree table and lists parent nodes as well as branch links. And the cluster table has a date and clustering method field. So you can put here, for instance, a SNP threshold for linking two samples with each other. You can then combine these tables to form a simple outbreak investigation with just a few lines of code. In this example, the criteria for a cluster is less than or equal to 2 SNPs difference in at least 3 samples collected after January 1st, 2024. You can identify the source case based on dates and the genetic diversity in a region. So this is very simple code, but imagine being able to do that in real time across every health system that is part of your multi-center surveillance system. Very powerful. Moving on to pillar 2, LLMs. So these models have revolutionized our ability to parse text at a large scale. They directly address a major problem in the field, which is that the same concept can be transcribed in many ways and in many languages. For instance, in free text notes, a patient with flu may be described as influenza A H3N2 detected, or just flu A positive. Genomic data for a variant may state BA.2.86 or Omicron variant, or spike protein S R346T. Similarly, treatment failure in HIV can be written as VL or viral load greater than 200, or treatment experienced with detectable viral load, or just virological failure. Even when existing vocabularies exist, say with low rank codes, there is variability between humans as to how the same concept is mapped to a code. Traditionally, humans have handled this variation using manual mapping tables and maybe a set of pre-coded rules. The problem with that approach is that it's very labor intensive to have to maintain these manual mappings, and they have to be updated as variations are encountered. The LLM approach requires you to build a set of prompts and maybe provide a few examples for proper mapping, and then allow the model to perform mapping automatically and periodically to update. Recent research has shown it can understand similarities between concepts very well and allows for translating from multiple languages to a common terminology. Furthermore, as I will show in the next slide, you can build a deployment architecture that allows it to learn over time and improve. Finally, it is much more robust to new terminology as new variants or even entirely new pathogens emerge. There are many ways you can design an LLM to aid in data harmonization, and I'm showing you just one, which leverages the use of AI agents tasked with various responsibility, where an agent is a separate LLM. The first agent's job in this example is just to extract relevant information from raw data. This may include virus names, antivirals, state of immunocompromise, or vaccination status. The second agent's responsibility is to map those extracted concepts to the OMOP common data model, which itself uses SNOMED, LOINC, RxNorm, etc. The third agent performs a validation check to ensure the mappings make sense and can be engineered to flag inconsistencies for human review. An example will be if a viral variant is mapped to a lineage that doesn't make sense. And finally, a fourth agent can be tasked to work with domain experts to incorporate their feedback into its output. And this can be done on a regular basis using a simple graphical user interface and has been shown by many research groups to greatly improve its performance over time. There are many things to consider when deploying LLMs for sensitive tasks. I propose some potential strategies here. In terms of developing the initial version of the model, it may make sense to start with a gold standard commercial model so that you can get a sense of how well it does on a given task. And once you find a set of suitable prompts or architecture, you can download an open source model like Llama 3 or now Google's MedGemma to perform inference locally. This would help support privacy as no data would be needed to be uploaded into the cloud and would be much cheaper. Fine-tuning can then be performed using the agent-based approach on the local model. In terms of arriving at the correct prompts, a standard strategy is to help the model out with a few examples of right answers stored in a RAG database. It can then reference these when it encounters the same mapping problem in real data. You can then add additional layers of reasoning to help navigate complex concepts like how to map a SARS-CoV-2 pango lineage to a WHO classification. The prompt can direct the model to output its response in a structured format like JSON. Finally, quality assurance can be built in using a human in the loop when models flag their uncertainty about a mapping, and also by comparing to existing benchmarks. Unfortunately, there are not that many out there currently. Random audits should also be included so that we're not dependent on the model itself to flag problems. Here's a hypothetical example of how an LLM agent-based system could work. Imagine you have a snippet of a virology report written in Dutch, and here it says SARS-CoV-2 PCR positive, CT VARDA 18.5, sequencing Omicron variant, JN parentheses JN.1, spike mutations, so on and so forth, aanwezig, meaning present. The extraction agent would parse that into the fields shown in the orange box, and the mapping agent would parse it into the fields shown in the blue box. So not only putting it into structured fields, but also translating it into English. Finally, a validation agent or a human could validate this output as shown in the box at right. The last pillar of my multi-center analytic approach directly addresses the issue of privacy. Some label this as a paradox since robust generalizable models require large, diverse datasets that cover many types of patients coming from a wide range of backgrounds. But patient data cannot be transferred freely through institutions, and for good reasons. These include regulations like the GDPR, local government laws, and ethical concerns, which are particularly relevant for sensitive health information. The traditional approach to handling this was to centralize the data using a secure linkage system and have strict governance. This is problematic because A, it takes a very long time to build that governance structure. B, if the central data lake is breached, everyone's data is compromised. C, for networks containing possible adversarial actors, there will be inherent trust issues. And D, ultimately, data is still being transferred out of the healthcare system's environment. The federated solution to this is to transport the model to the data rather than the reverse. The idea was actually first developed by Google, as was the architecture behind LLMs. And in this approach, data never leaves the source institution, which permits total control by host institutions and supports regulatory compliance. This will be an optimal approach to analysis of HIV cohorts, for instance. I illustrate conceptually how this works here. The first step in the process is to build a skeleton model and store it on the servers of a coordinating institution. Then, in step 1, this empty model is then distributed to each participating center. And in step 2, each center trains the model on their local data. And in step 3, the model parameters are sent back to the coordinating institution where a new consensus model is built. Typically, this involves generating a weighted average of the center-specific models. For a standard regression model, the data that is transferred, for instance, are the beta coefficients. The final step is to repeat steps 1 through 3 until the parameters converge onto their final values. As noted, only gradients for neural networks or weights for traditional regression model are shared, not actual patient data. And lots of studies have shown federated models to perform as well or nearly as well as those trained on a central data lake. In fact, this is the approach that Apple uses to model data from your cell phone. I've simplified what it takes to do this, but I list here several key components. You obviously need a coordination server that contains a central model and sends it out to participating centers. You need multiple high-performance computing clusters to train models at each center. You need a secure method for exchanging model parameters, and you need an agreed-upon method for generating the consensus model, which is usually a weighted average. Many federated networks have additional security measures that are shown here, with differential privacy being the most common. These are necessary because it is in theory possible for a malicious agent to recreate original data just from the model parameters. I don't think this will be a major issue in a network of healthcare institutions, but I think it is important to utilize some of these so that the network remains at least at an industry standard. So using those 3 pillars, I provide some examples of what can be done using this system. For instance, you can do respiratory virus prediction models that forecast flu, RSV, COVID-19 waves. You can account for local vaccination coverage and demographics in these models and have an early warning system for community transmission surges. You can also do viral variant detection as they emerge, to identify new variants across institutions. You can do phylogenetic clustering and tree building without having to share sequences, and of course, real-time surveillance for immune escape mutations. You can do co-infection and syndemic patterns, so bacterial virus interactions, as I stated earlier, immunocompromised patient outcomes, or subgroup analyses for other rare disease or rare patients. And finally, for HIV treatment specifically, you can predict virological failure risks with larger sample sizes, optimize ART regimens, and learn from diverse populations while protecting privacy. And finally, I'm showing this to visualize how it worked when it is all put together. Starting in the upper left-hand corner, data is generated at each participating hospital. Each hospital then deploys an LLM locally to extract and map their data to the common data model. It doesn't necessarily have to be the exact same LLM with each hospital. It can be different ones with different prompts. The common data model databases are updated at each institution with mutually agreed upon extensions and populated with the LLM output. Then federated learning is scheduled on a periodic basis, perhaps weekly for respiratory viruses or over longer periods of time for HIV cohort modeling. Centers then transfer model parameters back to the coordinating center, and the consensus model is then used by each center to provide robust, generalizable clinical decision support. The performance of the consensus model is then addressed by the coordinating center with support from the local centers. Finally, a feedback loop is built in to constantly improve the LLM performance and monitor models. The result is an always-on, self-improving surveillance and prediction system, something that is truly next generation and critical to handling emerging pathogens and perhaps the next pandemic. So this all looks great on screen, but there are lots of challenges to do this successfully in the real world. I list some of the technical ones on the left and the organizational ones on the right. I won't go through all of these, but I will say that there are potential solutions to all of them. They may not be easy to do, but they do exist. And how will we know if the system is working? Like before, there are multiple categories of metrics that apply to each different perspective we may have. For instance, a technical metric for success will be how often terms are being correctly mapped to categories, or how often the system is operational and generates data reports. From a clinical perspective, metrics for success will be how fast waves of respiratory viruses are identified compared to, say, a traditional baseline, or how fast variants in antiviral resistance are detected. At an organizational level, success will be how many centers elect to participate, which is highly relevant since the more that are involved, the better the models get. Other metrics include the volume of data harmonized and the cost per institution, which should go down over time. There are many examples of common data models, large language models, and federated learning networks out there, and I list a few of the general ones on the left. They include the Odyssey Network, Health Chain Project, which is EU-based, Pioneer Project, Google Health, and Melody. There are a few virology-specific ones on the right, such as GISAID, ECDC, IDEA, Eurocord, and NextTrain. However, it is important to note that none of these contain all the three pillars that I described here, which means there's a huge opportunity to innovate in the space. So with that, I thank you for listening and happy to take any questions during the Q&A period. Thank you.